There is something out there that shouldn't exist, something the James Webb Space Telescope pointed its golden mirrors toward in the dead silence of space, and what came back shouldn't have. Not by our models, not by our equations, not by anything written in any physics textbook currently sitting on any shelf in any university on Earth. And the scientists who saw it? They didn't celebrate. They went quiet. In the deep field images returned by humanity's most powerful eye, there are objects that glow with a brightness that defies conventional stellar physics. Objects so luminous, so massive, so impossibly ancient that the only way to explain them, the only model that even comes close, requires invoking something that has never been directly detected, something that makes up 27% of the entire universe. Something that passes through walls, through planets, through your body right now, without leaving a single trace. Dark matter. A question is quietly unsettling astrophysicists. What if dark matter didn't just surround the first star, but was the first star? What if the universe's earliest light wasn't born from hydrogen and helium, but from the destruction of something far stranger, the most mysterious substance known to exist? What did the James Webb Space Telescope really see? And why are scientists famous for caution now using words like extraordinary and unexpected? We're about to explore the answer. If you love the content, leave a like and subscribe to the channel. Get ready, we begin. To understand what the James Webb Space Telescope may have discovered, you first need to understand what it was built to do. Because JWST wasn't designed to find anomalies. It was designed to find origins. It was designed to stare so deep into the cosmic past that it would effectively see the universe as it existed in its infancy, in that raw, turbulent era, just a few 100 million years after the Big Bang, when the first structures were pulling themselves together out of a sea of hydrogen gas and darkness. The telescope is, in almost every measurable sense, an extraordinary machine. Its primary mirror stretches 6.5 meters across, nearly 3 times the diameter of the Hubble Space Telescope, and it operates not in visible light, but in the infrared spectrum. This matters enormously. Because the universe is expanding, the light from the most distant, most ancient objects gets stretched as it travels across billions of light years toward us. Visible light becomes infrared. And so to see the first stars and galaxies, you need eyes built for the infrared. JWST has those eyes. It orbits the Sun at what's called the second Lagrange point, nearly 1.5 million miles from Earth, positioned so that the Earth, Moon and Sun are always on the same side of it. This allows its massive sunshield, a 5-layer structure roughly the size of a tennis court, to block out heat and light, keeping the telescope cold enough to detect the faintest warmth of ancient starlight. We're talking about operating temperatures colder than -233 degrees Celsius, colder than almost anywhere in the known universe. All of this engineering, all of this precision, all of this cost roughly $10 billion over 3 decades of development, was aimed at answering one of the most profound questions humanity has ever asked. How did the first stars ignite? And in the first year of its scientific observations, JWST began returning answers. But some of those answers looked deeply, profoundly wrong. The problem wasn't that the telescope was broken. The problem wasn't a miscalibration or a software glitch or a smudge on a mirror. The problem was that what JWST found in the early universe, the objects that burned brightest in that ancient darkness, were too big, too bright, and too early. They were there when they shouldn't have been. And the mainstream explanations for how they got there are, to this day, actively contested. So what were they? Act 2. The universe that broke the model. Let's talk about the standard model of cosmology for a moment, because you need to understand what it predicts before you can appreciate how thoroughly JWST has complicated it. According to our best current understanding, the universe began approximately 13.8 billion years ago in an event we call the Big Bang. In the first fraction of a second, an almost incomprehensible amount of energy exploded outward, and as it cooled, it formed the basic building blocks of matter: protons, neutrons, electrons. The universe then entered a long dark period, known appropriately as the Cosmic Dark Ages, in which hydrogen and helium gas drifted through space without yet forming anything luminous. This period lasted, according to our models, for somewhere between 100 million and 200 million years. Then slowly, gravity began doing its work. Tiny fluctuations in the density of matter, quantum fluctuations, stretched to cosmic scales during a period of rapid early expansion called inflation, began pulling gas together into clumps. Those clumps grew, accumulated more gas, collapsed under their own gravity, heated up, and eventually ignited. Nuclear fusion. The first stars were born. This process, according to every simulation we have run and every model we have built, should take time. Structure doesn't form overnight. The very first stars, called population 3 stars in astronomical terminology, are expected to have been massive, hot, and short-lived, but they should have formed individually or in small clusters, and the galaxies that formed around them should have started small, building up gradually through mergers and accretion over hundreds of millions and then billions of years. That's what the model says. That's what every cosmological simulation predicted before JWST launched. Then JWST started looking. What it found instead were galaxies fully formed, surprisingly massive, surprisingly bright galaxies at redshifts of 10, 11, 12, and beyond. These are redshifts corresponding to a universe that was only about 300 to 500 million years old. The galaxies weren't supposed to be there, not in that form, not at that size, not at that brightness. Some of them contained as many stars as our Milky Way, which took over 10 billion years to build, and yet they were sitting there in a universe barely out of its infancy. Astronomers call this the impossibly early galaxy problem, and it has sent legitimate shockwaves through the cosmological community. Papers have been published, conferences have been convened, explanations have been proposed and debated and argued over with the barely restrained intensity that characterizes scientists who know they are looking at something that genuinely does not fit. Some researchers argue that these galaxies aren't actually as massive as they look, that there are selection effects, that JWST is preferentially detecting the brightest objects and we're not getting the full picture. Others argue that star formation in the early universe was simply more efficient than our models allow, that under the conditions of the early cosmos, gas collapsed and formed stars at a rate that our simulations underestimate. These are reasonable scientific arguments. They are being seriously debated. But then there's a third possibility, a possibility that, until recently, existed mostly on the fringes of theoretical astrophysics. A possibility that has now been raised by credentialed researchers in peer-reviewed journals, pointed directly at the anomalous objects JWST has detected. What if some of those objects aren't made of ordinary matter at all? Act 3. The idea that dark matter could burn. To understand what a dark matter star is, and whether JWST might have found evidence of one, you need to understand what dark matter actually is. Or more precisely, you need to understand how little we know about it. Here is what we know for certain. Approximately 27% of the universe, by energy content, is made of something that does not emit light, does not absorb light, and does not interact with normal matter through any of the forces we can directly detect, not electromagnetism, not the strong nuclear force, not the weak nuclear force. It only interacts through gravity. We know it's there because of what it does to the things we can see. Galaxies spin in ways that only make sense if they're embedded in enormous invisible halos of extra mass. Light bends around galaxy clusters in patterns that require far more gravitational lensing than visible matter alone could provide. The large-scale structure of the universe, those immense cosmic webs of galaxies and filaments and voids, only matches our observations if we include this invisible component. We know it exists. We just don't know what it is. The leading candidate for decades was a class of particles called WIMPs, weakly interacting massive particles. These are hypothetical particles that have mass, interact via gravity and the weak nuclear force, and should, in theory, be detectable by sufficiently sensitive underground detectors. Multiple billion-dollar experiments have searched for them. Multiple extremely sensitive detectors, buried deep beneath mountains and beneath the ocean floor, have listened for them. None have found a single confirmed WIMP. Other candidates include Axion's extremely light particles, originally proposed to solve a different problem in physics and sterile neutrinos, and primordial black holes, and a dozen other theoretical constructs, each with their own advocates and their own experimental programs. None have produced a confirmed detection. So we are in the strange position of knowing, with extraordinary confidence, that 27% of the universe is made of something we cannot identify. And in that context, in that landscape of profound uncertainty about what dark matter actually is, a particular class of theories about the early universe becomes very interesting indeed. The theory of dark matter stars, sometimes called dark stars, a term that carries its own haunting resonance, was first proposed in a serious, peer-reviewed form in 2008 by a team of researchers led by theoretical astrophysicist Fries Catherine, along with collaborators Douglas Spolier and Paolo Gondolo. Their paper, published in the journal Physical Review Letters, laid out a coherent mechanism by which the very first stellar objects in the universe might have been powered not by nuclear fusion, but by dark matter annihilation. Here is the core of the idea. In the earliest periods of the universe, before the first stars ignited, the density of dark matter was much higher than it is today. As gas clouds began collapsing gravitationally to form the first stellar objects, they were collapsing into regions of space that were also dense with dark matter. Now, if dark matter is made of particles that are their own antiparticles, a property called being Majorana particles, which WIMPs are theorized to have, then when two of these particles meet, they annihilate each other, converting their mass directly into energy via Einstein's famous equation. In a sufficiently dense dark matter environment, this annihilation produces energy at a rate that can actually halt the gravitational collapse of a protostellar cloud. Instead of the cloud continuing to compress and heat up until nuclear fusion ignites, it reaches an equilibrium, a stable, diffuse, cool object held up by the pressure generated by dark matter annihilation happening within it. A dark star. The theoretical properties of these objects are remarkable. Because they don't need to compress to nuclear fusion temperatures to generate energy, they can be far more diffuse than normal stars. Their theorized radii are on the order of astronomical units, meaning a single dark star might be as wide across as the distance from the Earth to the Sun, or even larger. But they can also be extraordinarily massive, potentially accumulating hundreds of thousands or even millions of times the mass of our Sun. And because they're powered by dark matter, which is abundant in the early universe, they could burn for millions of years without exhausting their fuel source, growing larger all the while. They would also be, crucially, luminous. Extraordinarily luminous. A dark star powered by the annihilation of a sufficient quantity of dark matter would shine with a brightness that might rival or exceed that of an entire galaxy of ordinary stars. And that brightness, that specific extraordinary luminosity, combined with the particular spectrum of light such an object would emit, is precisely what makes JWST relevant. If dark stars existed in the early universe, JWST should, in theory, be able to see them, or at least to see objects that are consistent with what dark stars would look like. ASTI 4. The candidates. 3 objects that shouldn't exist. Now we get to the specific evidence. In July 2023, a research team led by Catherine Fries, the same researcher who co-authored the original dark star proposal 15 years earlier, published a paper in the Proceedings of the National Academy of Sciences that examined 3 objects detected by JWST in its early deep field observations. The objects are designated by their technical catalogue names: JADES GSZ 130, JADES GSZ 120, and JADES GSZ 110. These aren't evocative names. They don't tell you anything about what they are, but the numbers at the end of each designation matter, because those numbers are redshifts. A redshift of 11 means we are seeing light that left its source when the universe was roughly 420 million years old. A redshift of 12 pushes that back to about 370 million years. A redshift of 13 takes us to approximately 330 million years after the Big Bang. These are extraordinarily early epochs. We are looking through JWST's infrared eyes at objects that were burning in the universe's first few percent of its total current age. And what we see, in all 3 cases, is something that makes the numbers not work. These objects are too bright. Not slightly too bright, dramatically too bright. The luminosity implied by their brightness at their given distances is enormous. And when researchers tried to model what could produce that luminosity, they found a significant problem. The mass of a conventional galaxy that would need to exist to generate that much starlight is implausibly large for objects that formed so early. The standard galaxy formation models simply cannot build something that bright, that fast. But here's where the dark star hypothesis enters the picture with unsettling precision. When Fries and her colleagues ran the numbers on what a dark star would look like, what its spectrum, its luminosity, and its apparent size would be, at those redshifts they found that all 3 objects were entirely consistent with the dark star model. Not merely marginally consistent, strikingly consistent. A single supermassive dark star, or perhaps a small cluster of them with a mass somewhere between 400,000 and 1 million solar masses, powered by dark matter annihilation, would appear from our vantage point, through JWST's instruments, essentially identical to what these 3 objects actually look like. The spectra match, the luminosities match, the colour profiles match. The paper was careful, as all good science is, to note that consistency is not confirmation. These objects could still be early galaxies with unusual star formation histories. They could be objects whose properties we're misinterpreting due to incomplete data. The dark star hypothesis is not the only explanation on the table, but it is, and the researchers are explicit about this, a plausible explanation that cannot be ruled out with currently available data. And that phrase "cannot be ruled out" in the universe of astrophysics is not a phrase that scientists use lightly. When a theoretical physicist says that their exotic, unconventional model cannot be ruled out, they are saying something significant. They are saying that the data leaves room, that the window is open, that the universe might actually be doing something stranger and more wonderful than we assumed. Let's sit with that for a moment. We have 3 objects, 3 bright, ancient, anomalous things burning in the early universe. 3 data points that don't fit the standard model of galaxy formation, and we have a theoretical prediction made 15 years ago, before JWST existed, before these objects were detected, that says dark stars of a specific type would look exactly like this. That is not nothing. ACT5. The dark matter. We never caught before we go further with what JWST may be telling us. It's worth pausing to confront something deeply unsettling about the dark matter story itself. Because the history of dark matter research is a story about a substance that has been predicted, theorized, modeled, and hunted for decades, and that has slipped through every net we've ever cast for it. The original evidence for dark matter goes back further than most people realize. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma galaxy cluster, a gravitationally bound collection of hundreds of galaxies, and found that the galaxies were moving far too fast. The gravitational pull of all the visible matter in the cluster wasn't sufficient to hold it together at those velocities. The cluster should have flown apart long ago. Zwicky concluded that there must be large amounts of invisible mass, what he called Dunkelmaterie, dark matter holding the cluster together. His conclusion was largely ignored for decades. In the 1970s, astronomer Vera Rubin, working with collaborator Kent Ford, was studying the rotation of individual spiral galaxies and found the same problem on a smaller scale. Stars at the outer edges of spiral galaxies were orbiting the galactic center far too quickly. According to Newtonian gravity and the distribution of visible matter, those outer stars should orbit slowly, just as outer planets in our solar system orbit the Sun more slowly than inner ones. But they didn't. They orbited at roughly the same speed as stars closer in, implying that the galaxies were embedded in a halo of invisible mass extending far beyond the visible disk. The pattern was unmistakable and universal. Every spiral galaxy Rubin examined showed the same anomaly. Dark matter, whatever it was, wasn't a local peculiarity. It was a feature of every galaxy in the universe. By the 1980s, the theoretical framework had been developed. Cold dark matter slow-moving, weakly interacting massive particles became the standard cosmological assumption. Simulations incorporating cold dark matter produced large-scale structure that beautifully matched the observed universe. The cosmic web of filaments and voids, the distribution of galaxy clusters, the statistics of the cosmic microwave background, all of it was consistent with cold dark matter. And then began the hunt. The experiments multiplied. The detectors grew more sensitive. The underground laboratories shielded from cosmic rays by miles of rock, filled with tanks of liquid xenon and germanium crystals and silicon detectors, each one listening for the telltale kick of a WIMP bouncing off an atomic nucleus. The Large Hadron Collider in Geneva was partly designed with the expectation that colliding protons at high enough energies might produce dark matter particles that would leave missing energy signatures in the detectors. Nothing. Lux, Xenon 1T, Panda X, L, Z, some of the most sensitive particle detectors ever built, have searched through years of data and found no confirmed dark matter events. The LHC has produced no dark matter candidates in any of its runs. Experiment after experiment has come back empty, and each null result has progressively squeezed the allowed parameter space for WIMPs, ruling out more and more of the mass and interaction cross-section combinations that theorists had hoped to detect. This doesn't mean dark matter doesn't exist. The gravitational evidence is overwhelming and undeniable. But it does mean that our best guesses about what dark matter is made of are, one by one, being challenged. And in that context, in the context of a substance that is cosmically pervasive, but experimentally invisible, the idea that it might do something unexpected in the extreme conditions of the early universe becomes not just speculative, but scientifically necessary to consider. Because if dark matter isn't what we thought it was, then the early universe wasn't what we thought it was. And if the early universe wasn't what we thought it was, then JWST, might be looking at the evidence of that difference right now. AST6, how a dark star is born and why it's unlike anything you've imagined. Let's construct the birth of a dark star, step by step, because the process itself is one of the strangest and most fascinating things in all of theoretical astrophysics. We're going back in time. Approximately 200 million years after the Big Bang, the universe has cooled. The cosmic microwave background has been emitted and is drifting away. Hydrogen gas fills space in a nearly uniform haze with only tiny density variations. Dark matter at this point is everywhere, filling the universe in smooth halos, denser in some regions than others, following the gravitational wells that quantum fluctuations seeded during inflation. In a region slightly overdense, in both ordinary matter and dark matter, gravity begins to win. The gas starts to fall inward. The dark matter halo deepens. As the gas cloud contracts, it drags more dark matter with it, not through any direct interaction, but through gravity, the only force dark matter responds to. The dark matter density at the center of the collapsing cloud begins to rise. In the standard picture, this is where things proceed straightforwardly. The gas continues to collapse. The core heats up, and eventually the temperature and pressure become high enough to ignite nuclear fusion. A star is born. But in the dark star scenario, something intervenes before that happens. As the dark matter density at the center of the cloud climbs above a critical threshold, dark matter particles begin annihilating with each other at a significant rate. If dark matter is indeed composed of Majorana particles, particles that are their own antiparticles, then any dark matter particle that encounters another will annihilate, converting their combined mass into energy, primarily in the form of quarks and leptons that quickly decay into gamma rays, neutrinos, and other particles. Most of those gamma rays and energetic particles don't escape the cloud. The surrounding gas is dense enough to absorb them, heating the gas and generating outward pressure. And here is the critical point. This pressure is sufficient to halt the collapse. The dark matter annihilation energy deposition rate equals the gravitational energy release rate, and the cloud reaches an equilibrium. It stops collapsing and becomes a stable, diffuse, dark matter-powered object. This object is a dark star, and its properties are extraordinary because it doesn't need to achieve nuclear fusion temperatures to generate energy. It's powered by annihilation occurring throughout its volume rather than fusion in a compressed core. A dark star doesn't compress to the density and temperature of a normal star. It stays diffuse, extraordinarily diffuse. The theoretical models suggest that a first-generation dark star might have a radius of approximately 1 astronomical unit, the distance from the Earth to the Sun, while containing only about 1 solar mass of material. This makes it about 1 million times less dense than our Sun, but still luminous due to the energy input from dark matter annihilation. Its surface temperature, by stellar physics standards, would be relatively low, around 10,000 Kelvin, compared to the Sun's roughly 5,500 Kelvin surface temperature. But its enormous size means its total luminosity could be comparable to or greater than that of the entire Sun. That's the first generation. But the story doesn't end there. As the dark star sits in its dark matter halo, it continues to accrete. More gas falls onto it from the surrounding cloud. The dark matter halo continues to supply fresh dark matter particles to feed the annihilation engine. The dark star grows and grows and keeps growing. The theorized end state of this process, a supermassive dark star that has accreted material for millions of years, is a genuinely mind-bending object. The models suggest upper limits on the order of 10 million solar masses. An object 10 million times more massive than our Sun, powered by dark matter annihilation, with a radius on the order of tens of astronomical units, shining with a luminosity potentially approaching that of a small galaxy. This is not a marginal, barely detectable object. This is one of the most luminous things in the universe. And when you ask, what would this look like to JWST, observing it from billions of light years away through 13 billion years of cosmic time? The answer, according to the theoretical models, is that it would look like a bright, point-like or near point-like source at an extreme redshift, with a spectral energy distribution consistent with a hot, massive, single object rather than the complex multi-component spectrum of a galaxy full of diverse stellar populations. Which brings us back with unavoidable weight to those three JADES objects. Act 7. The skeptics and their arguments. At this point, we need to do something that good science demands and good storytelling requires. We need to seriously engage with the skeptics, because the scientific community has not, by any stretch of the imagination, declared that JWST has confirmed the existence of dark matter stars. The debate is real, it is ongoing, and the counter-arguments are substantial. The most prominent alternative explanation for the anomalously bright early objects that JWST has detected is what might be called the enhanced star formation efficiency hypothesis. The argument is straightforward. Our models of how efficiently gas turns into stars in the early universe may simply be wrong. Standard models assume that only a fraction, typically a few percent of the gas in a collapsing cloud, actually ends up in stars. The rest gets blown away by stellar feedback, supernova explosions, radiation pressure, and other disruptive processes. But in the early universe, the conditions were different. Metallicity was lower. Gas cooling mechanisms were different. The cosmic environment was more homogeneous. It's plausible, the argument goes, that early star formation was simply more efficient, perhaps dramatically more efficient than our models predict, and that this higher efficiency can explain the large stellar masses implied by JWST's early galaxy detections without invoking any exotic physics. This is a serious argument. It's supported by some observational evidence from studies of star formation in extreme environments in the local universe, and several groups have published simulations showing that tweaking the star formation efficiency parameter can reproduce at least some of the JWST observations. The problem is that in some cases, the required efficiency is implausibly high, approaching or even exceeding 100% in some extreme examples, which is physically impossible, suggesting that even enhanced star formation efficiency may not be the complete answer. Another class of alternative explanations focuses on the masses themselves. When JWST observes a distant galaxy, it doesn't directly measure the galaxy's mass. It measures the galaxy's brightness. Converting that brightness to a mass requires assumptions about the stellar initial mass function, about the stellar populations present, about the fraction of light that might be coming from active galactic nuclei rather than stars. If early galaxies were dominated by very massive, very hot, short-lived stars with a different initial mass function than we assume, or if some of their light comes from active black holes in their centers, the inferred masses might be significantly overestimated. These are legitimate measurement uncertainty arguments, and researchers are actively working to test them with more detailed spectroscopic observations. JWST's NIR SPEC instrument can, in principle, measure the spectra of individual objects well enough to distinguish between a galaxy full of stars and other types of luminous sources. But this analysis takes time. It requires sufficient signal-to-noise, and for the faintest and most distant objects, it remains a work in progress. A third category of skepticism attacks the dark star hypothesis more directly. Critics point out that the dark star model makes assumptions about dark matter that themselves remain unproven specifically. The Majorana particle assumption that dark matter particles are their own antiparticles and will annihilate when they meet. If dark matter is not of this type, the entire annihilation mechanism that powers dark stars doesn't work, and the hypothesis collapses. Furthermore, even if dark matter is the right type, the efficiency of the annihilation process and the ability of the dark matter halo to maintain a sufficient density in the star's interior as the object grows are uncertain and depend on detailed models of dark matter dynamics that are themselves contested. There's also a general statistical concern. The three JWST objects that Fries and colleagues highlighted are anomalous, but they are only 3 objects. In any survey of thousands of objects, you expect some outliers. The question of whether these 3 objects represent a genuinely new class of phenomenon, or simply the bright tail of a distribution of ordinary but unusually massive early galaxies, is one that requires much more data to answer. All of these arguments are valid. None of them prove that the dark star hypothesis is wrong, and none of them fully explain the anomalies either. This is exactly the situation where science is supposed to be. Confronted with observations that don't fit existing models, generating multiple competing hypotheses, and gathering more data to distinguish between them. The honest scientific answer right now is, we don't know. But the dark star hypothesis is on the table, and the fact that it was predicted before JWST launched and that the predictions match the observations means it cannot be dismissed. Act 8. The deeper mystery. What comes after a dark star? Here's where the story takes another turn into territory that should genuinely unsettle you, because the question of what dark matter stars eventually become opens a door onto one of the other major unsolved problems in astrophysics: the origin of supermassive black holes. At the center of virtually every large galaxy in the universe, there is a supermassive black hole. Our own Milky Way has one Sagittarius A star with a mass of about 4 million solar masses. The galaxy M87, famously imaged by the Event Horizon Telescope, has a central black hole of about 6.5 billion solar masses. These objects are enormous, and they are ubiquitous, and we don't have a convincing explanation for how they formed. The standard formation scenario involves a process called seeding. Small black holes form from the first generation of massive stars. They grow by accumulating gas and merging with other black holes over time, and eventually they reach supermassive scales. The problem is the timeline. JWST and its predecessor telescopes have found evidence of supermassive black holes with masses of hundreds of millions to billions of solar masses at redshifts corresponding to the universe being less than 1 billion years old. Growing a seed black hole of a few tens of solar masses to 1 billion solar masses in less than 1 billion years requires essentially continuous maximum rate accretion, which is physically difficult to achieve and arguably unrealistic under typical astrophysical conditions. This is the black hole mass problem, and it's been nagging at cosmologists for years. Dark stars offer a possible solution that is elegant in a deeply unsettling way. According to the theoretical models, a supermassive dark star, one that has grown through accretion to millions of solar masses, doesn't die the way an ordinary massive star dies. It doesn't run out of hydrogen and collapse into a neutron star or a small black hole. Instead, its fate is governed by the supply of dark matter available to fuel its annihilation engine. As the universe evolves and the dark matter halo disperses and thins out as other structures form and pull dark matter away, or as the halo's central density drops due to the dark star's own gravitational influence, the energy production from dark matter annihilation begins to decrease. Eventually, the dark matter fuel runs low, The outward pressure that has been holding the dark star up against gravitational collapse begins to fail. And when it does, there is nothing to stop the collapse. The entire multi-million solar mass object, this ancient, diffuse, cosmically bizarre entity, collapses directly into a black hole of comparable mass. A black hole of hundreds of thousands to millions of solar masses formed in a single catastrophic collapse event. This is called a direct collapse black hole in the literature, and it's actually a concept that was being seriously explored even before the dark star hypothesis, motivated precisely by the need to explain how supermassive black holes got so big so fast. The dark star scenario provides a plausible physical mechanism for how direct collapse black holes could form. First a dark star, then a direct collapse, then a supermassive black hole that can grow further by accretion. If this scenario is correct, then every supermassive black hole at the center of every galaxy in the universe, including the one at the center of the Milky Way, right now, sitting 26,000 light-years away from where you're reading. This might have begun its existence not as a collapsing star of ordinary matter, but as an ancient dark matter-powered object from the universe's infancy. A dark star that burned for millions of years in the cosmic dawn and then collapsed into darkness. The black hole at the center of our galaxy might be a dark star's corpse. That thought deserves a moment. Act 9. The cosmic dawn and the lights that changed everything. To fully appreciate the significance of dark stars, whether they existed or not, you need to understand the period of cosmic history in which they would have lived, the epoch of reionization. This is one of the most dramatic transformations the universe has ever undergone, and it remains one of the least understood. After the cosmic dark ages, that long period of hydrogen gas drifting through space without luminous sources, the first objects began to ignite. Whether those first objects were ordinary population 3 stars, dark stars, or some combination of both, they had one thing in common. They were pumping ultraviolet radiation into the universe. And that ultraviolet radiation began doing something important. Hydrogen atoms can be ionized, stripped of their electrons, by sufficiently energetic photons. When the first luminous objects began shining, their ultraviolet output started ionizing the hydrogen gas around them, creating bubbles of ionized plasma in the sea of neutral hydrogen. These bubbles grew, expanded, merged, and eventually, by about 1 billion years after the Big Bang, the entire intergalactic medium had been re-ionized. The universe went from opaque, neutral hydrogen absorbs ultraviolet light, to transparent, ionized hydrogen doesn't. This transformation, reionization, changed the universe fundamentally. It's why we can see as far as we can see with telescopes today. Before reionization, the universe was fog. After reionization, it became clear. The question of what drove reionization, what provided the photon budget to ionize every hydrogen atom in the intergalactic medium, is still actively debated. The candidates include the first generation of hot massive stars, early active galactic nuclei powered by accreting black holes, or some combination of both. And dark stars, if they existed in sufficient numbers, would have contributed their own luminous output to this process. But here's the thing that makes the dark star contribution particularly interesting to think about. Dark stars, according to the models, would have been the most luminous individual objects in the universe during this period. Far more luminous than any ordinary star, and potentially comparable to small galaxies. If they existed, they would not have been invisible. They would have been dominant features of the early cosmic landscape, burning brightly while everything else was still just gas and darkness. JWST was built in part to study the epoch of reionization. It was designed to look at that turbulent, transformative period and understand how and when and by what mechanism the universe went from dark to light. And in doing so, it is inherently searching, whether intentionally or not, in the exact time and place where dark stars, if they existed, would have been burning. The three anomalous objects identified in the Fries et al.'s paper are not random. They exist precisely in the redshift range Z, greater than 11, that corresponds to the earliest phases of cosmic dawn, the period before reionization was complete, when whatever was driving the first light in the universe was just getting started. Their location in cosmic time is not coincidental to the dark star hypothesis. It is the exact window where dark stars are predicted. This is important for understanding why researchers are taking the hypothesis seriously. It's not just that these objects are bright and anomalous, it's that they're bright and anomalous in the specific era where the theory says strange things should be happening. The anomaly and the prediction occupy the same neighborhood in cosmic time. That is meaningful even before any spectroscopic confirmation. Asked 10. What would proof actually look like? Science runs on falsifiability, a hypothesis that can never be tested, that can always retreat into unmeasured parameter space to avoid disproof, is not a scientific hypothesis. It's speculation. So the critical question, if we're going to take the dark star idea seriously, is what would proof actually look like? What observation would confirm that these anomalous JWST objects are dark stars? And what observation would rule them out? The most powerful tool available is spectroscopy, the analysis of how objects emit light at different wavelengths. Every type of object has a characteristic spectral signature, and dark stars are theorized to have a specific and unusual one. Because a dark star is powered by dark matter annihilation rather than nuclear fusion, its interior never reaches the temperatures necessary for the nuclear reactions that produce the heavy elements carbon, oxygen, nitrogen, and heavier species that show up as characteristic absorption or emission lines in stellar spectra. A dark star should show essentially pristine, metal-free spectra, dominated by hydrogen and helium and nothing else. Furthermore, the overall shape of its spectral energy distribution, how its brightness varies across wavelengths, should be consistent with a single, very hot, very diffuse photosphere, rather than the composite spectrum of many different types of stars at different temperatures. JWST's NIR spec instrument can, in principle, perform this kind of spectroscopic analysis. The challenge is signal to noise. These objects are extremely distant and therefore extremely faint, and obtaining a spectrum with sufficient detail to distinguish between a dark star and a very unusual early galaxy requires long exposure times. The observations have been proposed. Follow-up programs are planned or underway. The data will eventually come. There is also the question of spatial extent. Ordinary galaxies, even at high redshift, show some spatial structure in JWST's high-resolution images. They're not perfect points of light. They have detectable extent and internal structure. A supermassive dark star, despite its enormous physical size, would appear as an unresolved point source at cosmological distances due to the angular size it subtends, roughly comparable to or smaller than the resolution limit of JWST. If these anomalous objects are resolved, if they show clear evidence of internal structure, consistent with multiple stellar populations, that's evidence against the dark star interpretation. If they remain unresolved point sources, even under JWST's highest resolution imaging modes, that's consistent with, though not proof of, the dark star scenario. Additionally, dark stars should not show the emission line signatures of ionized gas that ordinary galaxies do. Galaxies contain ionized nebulae, H2 regions, active galactic nuclei, shock ionized gas that produce distinctive emission lines in spectra. Lyman alpha, O3, H beta, and others. These lines are, in fact, one of the primary tools astronomers use to confirm the redshifts of High's galaxies. A dark star would lack the internal ionized gas structures that produce these lines, so its spectrum should be relatively line-free compared to ordinary galaxies. If detailed spectroscopy of these JD's objects reveals a rich emission line spectrum consistent with an ionized galaxy, the dark star hypothesis becomes much less viable. If it reveals a smooth, line-poor continuum consistent with a single hot photosphere, the hypothesis gains significant support. These are concrete, testable predictions. JWST can, in principle, obtain the data needed to test them. The question is whether the available telescope time, the brightness of the objects, and the required observational depth make it feasible on a reasonable timescale. Given JWST's extraordinary sensitivity, there is reasonable optimism that definitive spectroscopic data on at least some of these objects will be obtained within the next few years of its operational lifetime. The universe has left us clues. We built a telescope capable of reading them. Now we need to look carefully. Act 11. The Physics of Annihilation. A closer look at the engine. The energy source that would power a dark star is, in its own way, the most efficient energy source theoretically possible. And understanding it helps you appreciate why dark stars could be so extraordinarily luminous. When two dark matter particles, assuming they are Majorana particles, annihilate each other, they convert their entire rest mass into energy. Every joule stored in both particles' masses becomes radiation and other high-energy products. This is total mass energy conversion, the theoretical maximum that Einstein's famous equation allows. By comparison, nuclear fusion, the process that powers ordinary stars, converts only about 0.7% of the mass of the hydrogen fuel into energy. The rest remains as helium ash. Dark matter annihilation is, in principle, more than 140 times more energetically efficient than the most efficient nuclear process we know of. The products of this annihilation depend on the specific type of dark matter particle involved. For WIMPs, the most studied candidate, annihilation typically produces pairs of quarks and antiquarks, which then quickly hadronize, forming p-ions, protons, and other hadrons, and subsequently decay into stable particles including photons, neutrinos, electrons, and positrons. The photons and electrons deposit their energy in the surrounding gas through interactions with the electromagnetic field, heating the gas and creating the outward pressure that supports the dark star against collapse. The neutrinos, frustratingly, escape almost completely. They barely interact with matter at all, so they carry energy out of the dark star without contributing to its support. This represents an energy loss term in the dark star's energy budget, and it affects the detailed calculations of how large and how luminous a given dark star can be. The theoretical models account for this neutrino loss, and even with it, the energy deposition rates from dark matter annihilation in a sufficiently dense halo are more than adequate to halt gravitational collapse and maintain a stable dark star. The efficiency of the process also depends critically on what physicists call the annihilation cross-section, a number that characterizes how likely two dark matter particles are to annihilate when they encounter each other. The canonical WIMP annihilation cross-section, derived from the requirement that WIMPs produce the correct cosmological dark matter abundance, is a number called the thermal relic cross-section, approximately 3 × 10 to the -26 cubic centimeters per second. This is the benchmark value used in dark star calculations, and it happens to be consistent with a dark star of sufficient luminosity to be detectable by JWST if the dark matter density in the star's interior is high enough. One of the most elegant aspects of the dark star theory is how it connects different lines of evidence. The same annihilation cross-section that is required to explain the cosmic dark matter abundance through thermal freeze-out in the early universe is also, independently, the value needed to produce dark stars with the properties necessary to explain JWST's anomalous detections. The theory doesn't require fine-tuning to make dark stars work at the observed luminosities. The numbers come out roughly right from first principles. That internal consistency is a feature that careful theorists look for and value. None of this is proof, but it adds to the picture of a hypothesis that, while exotic, is not arbitrary. Dark stars are not the product of theoretical desperation. They emerged from the natural application of known physics to the conditions of the early universe, and they make quantitative predictions that happen to overlap with anomalous observations. That combination is precisely what motivates serious scientific investigation. Act 12. The broader implications. If dark stars were real, step back for a moment from the specific objects, the specific redshifts, the specific spectral predictions. Step back and consider what it would mean for our understanding of the cosmos if dark matter stars were real, if the first lights in the universe were not fusion-powered but annihilation-powered. It would mean that the cosmic timeline we've constructed our narrative of how structure formed, how galaxies assembled, how the first elements were forged and spread through the cosmos is incomplete in a fundamental way. The story of cosmic chemistry, in particular, would need revision. Population 3 stars, in the Standard Model, are the first producers of heavy elements carbon, oxygen, silicon, iron, and everything heavier than hydrogen and helium. They form, burn briefly and brilliantly, explode as supernovae, and seed the universe with the building blocks of planets, of life, of chemistry as we know it. The second generation of stars forms partly from this enriched material, and the process of chemical enrichment cascades down through cosmic time until you get, eventually, a solar system rich enough in heavy elements to form rocky planets with complex geochemistry. If dark stars came first, if there was a population of enormous, long-lived dark matter-powered objects burning in the cosmos for millions of years before the first nuclear-burning stars ignited, then the chemical enrichment timeline would be different. Dark stars don't produce heavy elements through nuclear fusion, so their existence doesn't advance the chemical evolution of the universe. They may have actually delayed the onset of the chemical enrichment by displacing the formation of nuclear-burning stars for millions of years. This could have implications for the distribution of heavy elements in the early universe, for the timing of the formation of the first rocky planets, and potentially in the most extreme extension of the reasoning for the conditions necessary for the emergence of life. If dark stars are real and were cosmologically significant, the universe's biography needs a new chapter near the beginning. Not a small footnote, but a substantial addition that changes the narrative of what came before everything we have previously considered to be the beginning of cosmic chemistry. There is also the question of what dark stars mean for our understanding of dark matter itself. If we could confirm that objects in the early universe were powered by dark matter annihilation, it would constitute indirect but compelling evidence that dark matter particles do indeed annihilate, that they are Majorana particles, as theories like supersymmetry predict. This would be the first real observational constraint on the self-interaction properties of dark matter, obtained not from underground particle detectors or collider experiments, but from telescopes pointed at the ancient universe. In other words, dark stars, if confirmed, would be the most powerful dark matter detector ever discovered. Better than our Lux, better than xenon, better than the LHC, because they would be natural concentrators of dark matter, converting dark matter annihilation energy into starlight across scales of astronomical units, visible across billions of light years of cosmic distance. The irony is profound. For decades, we've built elaborate underground experiments to detect dark matter directly, one particle at a time, in the controlled quiet of a deep mine. And all along, the universe may have been building its own detectors, enormous, luminous, cosmically conspicuous ones right at the beginning of time. Detectors that were there all along, waiting for us to build a telescope sensitive enough to see them. JWST may be that telescope. Act 13. The competition. Other exotic hypotheses for the same anomalies. The dark star hypothesis is not the only exotic explanation that has been proposed for JWST's anomalous early universe observations. In the vigorous, sometimes contentious world of modern cosmology, anomalous data attracts theoretical attention the way light attracts moths, and several other unconventional ideas have been put forward to explain what JWST is seeing. One prominent alternative is the modified gravity class of theories. General relativity, our current best description of gravity, has been tested with extraordinary precision in the solar system and in strong field environments like binary pulsars and merging black holes. But on cosmological scales, the evidence is less direct. Some researchers argue that if the law of gravity behaves slightly differently on very large scales, if there are corrections to general relativity that become significant on galactic and cosmological scales, then the formation of structure in the early universe might proceed differently than our standard models predict, potentially explaining early massive galaxies without invoking dark matter or any other new particle physics. The challenge for modified gravity theories is that they struggle to reproduce the success of cold dark matter models in explaining the large-scale structure of the universe, the cosmic microwave background anisotropies, and the galaxy clustering statistics that have been measured with tremendous precision by surveys like SDSS and Planck. They also don't naturally explain the gravitational lensing observations that constitute some of the strongest evidence for dark matter. For most cosmologists, modifying gravity is a harder sell than modifying the dark sector. Another class of exotic explanations invokes primordial black holes that formed not from stellar collapse, but directly from density fluctuations in the early universe, before the first stars existed. If primordial black holes formed in significant numbers in the early universe, they could serve as seeds for rapid black hole growth, potentially explaining the supermassive black holes seen by JWST at high redshift. Some versions of the primordial black hole scenario also implicate dark matter. There is a hypothesis that dark matter itself might be composed of primordial black holes, at certain mass ranges that haven't yet been ruled out. There's also discussion of direct collapse black holes that form through mechanisms other than dark stars scenarios in which a massive gas cloud in an unusual environment, specifically one that is metal-free and illuminated by a strong Lyman-Werner radiation field that dissociates hydrogen molecules and prevents gas cooling, can collapse directly into a black hole without forming stars first. This scenario produces heavy black hole seeds that can grow more easily to supermassive scales. And there are more exotic proposals still, modifications to the initial conditions of the universe, new fields that affect structure formation at early times, non-standard inflation scenarios that produce enhanced density fluctuations on specific scales, and others. The landscape of theoretical cosmology is, at this moment, rich with competing ideas, all trying to account for JWST's surprising findings. What distinguishes the dark star hypothesis in this crowded field is a combination of specificity, prior prediction, and scope. It was predicted before JWST launched. It makes specific, quantitative, testable predictions about the spectral and morphological properties of the objects it predicts. and it potentially addresses multiple outstanding problems simultaneously: the anomalous brightness of early objects, the rapid growth of supermassive black holes, and the nature of dark matter within a single coherent framework. Other hypotheses may be simpler or more conservative, but few have the same combination of virtues. Act 14. The people behind the discovery. Catherine Frazee and the Dark Star Story. Behind every extraordinary scientific hypothesis, there are people. And the Dark Star Story is inseparable from Catherine Frazee, the theoretical astrophysicist at the University of Texas at Austin, whose career has been intertwined with dark matter physics for decades. Frazee first encountered dark matter as a graduate student in the early 1980s, when the field was young and the WIMP paradigm was just being established. She has spent her career developing theoretical models of dark matter and its cosmological implications, contributing to the development of what's called the WIMP miracle, the observation that a particle with the mass and interaction cross-section naturally predicted by supersymmetric theories also happens to produce, through thermal freeze-out in the early universe, approximately the right amount of dark matter to match the observed cosmological abundance. This coincidence, striking in its implications, was a major part of why WIMPs became the dominant theoretical paradigm. The dark star idea came to Frazee through a collaboration that began not in a physics department, but in a somewhat more informal setting. The specifics vary in different accounts, but the key intellectual contribution was the realization that dark matter annihilation in dense protostellar clouds would produce enough energy to alter stellar evolution in the first generation of objects. The paper she co-wrote with Spoliar and Gondolo in 2008 laid out the physics with sufficient rigor to be published in one of the most prestigious physics journals, and it sparked a significant theoretical program that has continued ever since. What is remarkable about the 2023 JWST paper, the one that pointed to the three JADES objects as potential dark star candidates, is that it closes a loop that took 15 years to close. A prediction made in 2008 in the theoretical dark, before the telescope existed, before the objects were detected, has met observational data that is consistent with it. Whether or not the dark star hypothesis ultimately proves correct, the fact that this is happening, that a prior theoretical prediction is engaging with actual telescopic data, represents the scientific process working as intended. Frazee herself has been careful in public statements to avoid overclaiming. She and her co-authors explicitly frame the 2023 paper as identifying objects that are consistent with the dark star model, not as proof. She acknowledges the alternative explanations. She calls for follow-up observations. This is the comportment of a scientist who believes in her hypothesis, but understands that belief is not evidence, and that evidence is what matters. The measured quality of this scientific engagement is, in its own way, part of the story. We are not in the realm of fringe science or extraordinary claims without extraordinary evidence. We are in the realm of legitimate theoretical physics confronting legitimate observational anomalies and asking carefully and rigorously whether a model made a decade and a half ago might be telling us something true about the universe. Act 15. The James Webb Telescope's unfinished conversation with creation. Cinematic wide-angle return. Visuals. Full JWST deep field cosmic scale perspective. Let's return to the telescope itself for a moment, because JWST is not finished, not by any stretch. It launched in December 2021 with enough fuel to operate for a minimum of 10 years and potentially significantly longer. The precision of the launch and the efficiency of the orbital insertion were so good that the fuel budget is expected to support operations well beyond the initial 10-year design lifetime. We are, as of now, only a few years into JWST's scientific life, and the data that has already come back has already upended multiple areas of astrophysics. The observations that have been used to identify potential dark star candidates represent only a small fraction of JWST's observational program. The telescope observes in multiple modes: imaging, spectroscopy, coronagraphy, and time series observations across multiple instrument packages, and it divides its time among hundreds of approved scientific programs covering everything from exoplanet atmospheres to nearby star formation to the most distant galaxies in the observable universe. The Early Universe program, while prominent and scientifically significant, is just one thread in a vastly rich observational tapestry. As JWST continues to accumulate data, the sample of high redshift anomalous objects will grow. More objects like the 3 JDS candidates will be identified. Better spectroscopic observations of the most promising candidates will be obtained. The statistical picture of the early universe, how bright it was, what it contained, where the luminosity came from, will sharpen from a blurred impression into a detailed portrait. And as that portrait sharpens, it will become increasingly possible to determine whether the anomalies are consistent with known physics pushed to its limits, or whether something genuinely new is required to explain what's there. The dark star hypothesis is, in this context, waiting for its verdict. The prosecution and defense are assembled, the evidence is being gathered, and the judge in this case, physics itself, will render a decision based on what the data actually shows. That decision may come in the form of a spectroscopic observation that definitively shows these objects to be ordinary, if unusually massive, galaxies. Or it may come in the form of a spectroscopic observation that shows something deeply strange, a metal-free line-poor continuum consistent with a single hot photosphere of extraordinary luminosity at a redshift that places it in the exact era where dark stars are predicted. Either outcome would be scientifically valuable. A ruling against the dark star hypothesis would still leave the anomalous masses and luminosities to be explained, driving further development of conventional models. A ruling in favour, or even strong support, short of definitive proof, would open one of the most extraordinary chapters in the history of astrophysics. It would mean that the first lights in the universe were not what we thought, that the cosmic dawn was lit by a physics we do not yet fully understand. Final act: the answer and why it's not the end. So let's return to the original question, the one that opened this documentary, the question that drove us through the history of dark matter, through the anomalies of the early universe, through the theoretical architecture of objects that burn without fusion. Did JWST discover dark matter stars? The careful, honest, evidence-based answer is this. JWST has found objects that are consistent with dark matter stars. It has identified 3 specific candidates: JADES GSZ 130, JADES GSZ 120, and JADES GSZ 110 that cannot be explained by conventional galaxy formation models without significant theoretical strain, and that match with striking precision the predictions of the dark star model made 15 years before JWST launched. The lead researcher on that original theoretical prediction has published peer-reviewed work arguing that these objects are genuine dark star candidates. That is not a confirmation. It is not proof. Science rarely delivers its verdicts all at once in a single dramatic announcement. It delivers them slowly, through accumulation, through follow-up, through the patient grinding of more data against theoretical predictions until the picture becomes clear enough that doubt becomes unreasonable. We are not yet at that point with dark stars. We are at the earlier, more intellectually alive moment, the moment where the hypothesis is viable, where the observations are consistent, where the extraordinary possibility has not been ruled out. In some ways, This is the best moment in science, the moment of maximum openness, before the answer arrives and closes the door on all the other possibilities that were once alive. But let's be clear about what is at stake if the dark star hypothesis is eventually confirmed. Not just supported, not just consistent with actually confirmed, it would mean that the first phase of cosmic stellar history was not hydrogen burning. It was dark matter burning. It would mean that for the first hundreds of millions of years after the Big Bang, the universe's most luminous objects were not powered by nuclear physics, but by the annihilation of an invisible substance we cannot yet directly detect. It would mean that the seeds of every supermassive black hole in every galaxy in the universe, including the one at the heart of the Milky Way, 26,000 light-years away, were dark matter constructs from the cosmic dawn. It would mean that life, which requires heavy elements forged in stellar nucleosynthesis, was delayed by this dark interlude, that the chemistry necessary for planets and biology was held back while the dark stars burned. It would mean that the universe's biography, which we have been writing with increasing confidence for a century, is missing a chapter, and not a minor chapter, the first chapter, the one where the lights first came on. And perhaps most profoundly, it would mean that dark matter, that's silent, invisible, intractable, 27% of everything, was not merely a passive scaffolding on which visible structure formed. It was, in the beginning, the active participant, the fuel, the fire. The universe did not just sit in a halo of dark matter. In the beginning, it may have burned with it. That thought is worth carrying with you. Not as a certainty, science doesn't give us those easily, and anyone who tells you differently is selling something, but as a genuine, open, live possibility. One that the most powerful telescope humanity has ever built may be in the process of answering, one observation at a time, in the cold infrared dark 1.5 million miles from Earth. The James Webb Space Telescope is still looking. The data is still coming in. The universe is still talking. We just need to keep listening. In the deep field images returned by JWST, in the infrared glow of objects so old they challenge our models and unsettle our certainties, there are 3 points of light that might be something entirely new, or they might be the most extreme examples of something familiar. The distinction matters enormously, and we do not yet know which it is. What we do know is this: the universe at its birth was stranger than we assumed. The first light that ever burned in the cosmos came from somewhere, powered by something, shaped by conditions we are only beginning to understand. Whether that something includes the annihilation of dark matter particles in primordial stellar objects. Dark stars burning in the cosmic dawn is a question that will be answered by data, by patience, by the slow, careful, beautiful process through which human beings, on a small planet, in an ordinary galaxy, in an unremarkable corner of the universe, try to understand where everything came from. JWST is our best tool for that process, and it is working. The lights were on at the beginning. We just need to understand what was burning. Stay curious. The universe is not done surprising us.